So I'm standing by now.
Okay. So,
okay. Thank you.
So, great. Well done. Very better. यहाँ से करोगे तो
We are live on YouTube now.
Shall we start, Yogesh?
Yeah, sure, absolutely.
So over to you.
Just a moment. Yeah. Good morning, everybody. Today we are privileged to have Professor Ajayan from Rice University as a speaker for the Institute lecture. Professor Ajayan is a pioneer in the area of nanotechnology. He's a Benjamin M. and Mary Greenwood Anderson Professor of Engineering and the founding chair of the Department of Material Science and Nanoengineering at the Rice University. He is also a distinguished visiting professor at IIT Kanpur. His work covers diverse areas of nanomaterials, including nanoparticles, nanotubes, two-dimensional materials, nanocomposite, and energy storage materials. Professor Ajayan is recipient of several awards, such as Spicer's Memorial Award, MRS Medal, and the list is too long to be mentioned in this particular introduction. He's an extremely prolific researcher. He has published more than 1100 journal papers and earning more than 100,000 citations with H index of 155. Even these numbers are mind-boggling. So today he's going to talk about striving for excellence in academic research, a case for nanomaterials innovation. Professor Ajayan, we are privileged to have you with us, and I request you to take the stage for giving a talk. My request to audience is please raise your hands, of course, in online mode once the lecture is complete if you have any questions. Otherwise, you can also put your questions in the chat box. Thank you so much. And now may I request Professor Ajayan to take the stage.
Thank you, Yogesh. I just want to make sure that you hear me well. Yep. Everybody? Okay. Let me first thank the organizers of this seminar. It's always a wonderful experience to come back to IIT Kanpur. And of course, as Yogesh said, I'm part of IIT Kanpur as well. And we do have a very special connection with IIT Kanpur, Rice and IIT. We had this MOU signed a few years ago. And the idea was to work with faculty here, have a strong bridge that allows exchange of students and so on between the two institutions, and ultimately build wonderful research experiences together. And of course, the pandemic kind of put a dampener on that, and hopefully things will pick up this year. And one of the main reasons for my visit is to initiate or reignite that whole idea of collaborative effort between IIT and RISE. Now today, the talk is a little bit, I should say, motivational. And in fact, recently I gave a very same or similar talk at IIT Hyderabad. The director of IIT Hyderabad asked me to give a motivational speech, and I never really done this in that sense before. So some of the things that I noted down in terms of what made my career and how perhaps the rules of what excellence could be is jotted down in this talk. And again, it's very personal perspective. And again, the excellence is an interesting criteria. And if you ask different people, the answers could be different. But there are certainly some common denominators that we all understand. And perhaps this talk is going to be based on those. Let's see. I mean, again, we can have a discussion in the end. Of course, RISE is one of those, really I should call boutique schools, a very small university in the middle of a large city, Houston. And among the top 20 universities in the US, we are perhaps one of the smaller ones, maybe the second or third smallest in that class of 20. So that kind of tells you that the numbers not always matter. It's the scholarship that you produce, it's the impact that you create that ultimately leads to excellence. And again, this talk is mostly going to be based on some of my experiences and observations in my career. So you will see some examples of research that is taken from my own research career. Let me try to move the slide. It doesn't seem to move. Oh no.
You can use the keyboard maybe.
Okay, I could use a keyboard. No, that's also stuff. No, we rely too much on technology, so
Yeah,
sometimes.
You can move the keyboard.
Okay, now it's moving. Does that move as well?
Quite a touch.
Yeah, okay. So before I start talking about specifics, let me say a few things about technology in general and engineering in general. The social impact of engineering is important, and as we go towards new technologies, we are realizing more and more that engineers or scientists should operate at the interface between science and society. And to be honest, if you think about what has really impacted social life in the past several decades, there is no better answer than technology and science. Right? The way we live has been completely changed because of the incursion of certain amazing technologies into our lives. All the way from mobile devices to Internet of Things. We don't act or behave the same way we used to 20 years ago, 30 years ago. I can still imagine, remember the time when I was a graduate student, undergraduate student and a graduate student, and we were really struggling with the very early word processing software. I think I wrote my thesis in one of the early softwares that was created by Microsoft, and it was a struggle. And you don't see that happen anymore. Or my PhD thesis did a lot of work in electron microscopy. So at least one day a week, I used to spend in a clean room, in a dark room, essentially to print pictures. Then we had to print the pictures, then essentially print several copies and paste them on papers before we send out for publication. But those things have completely changed. You don't see researchers working in microscopy go into the dark room anymore because everything is digital. Right? So there are many things that in front of our eyes have become almost obsolete, and many things that have come in a significant way that has changed our lives. And there are many other technologies that is going to do the same thing. If you think about genomics, for example, the whole idea of gene editing is going to completely change the way we are human beings. Right? So those kind of revolutionary things one has to really go back and say, wow, technology has done this. And one thing I wanted to also say is that although you essentially finally the impact comes from technologies, there is a foundational aspect to this. Many of the technologies that you see today had origins in some really beautiful, creative, foundational work. And in many cases, you look at electronics and related technologies, it all goes back to the significant impact of quantum mechanics, the whole that really romantic period around the war that really created the foundations of quantum mechanics is what has changed our lives. So you cannot really separate the foundational or fundamental science to real technological impact, because they're all connected. And there are many technologies that I will mention later on in my talk that started 30, 40 years ago in some lab as a creative invention and then slowly found its way into the marketplace. Right? So you cannot really not engage in foundational research if you were to make an impact in the long run. And of course, I'm fond of materials. My career has been in advanced materials, and many of these technologies do need materials as the platform. In fact, somebody said that those who control materials control technology. I think that is very, very important, whether it is silicon-based or whether it is carbon-based, or maybe in the future molecule-based. I think it's all the innovations in material science that allows you to practice high-end technologies. And I just wanted to give a glimpse of the kind of group that we have had over the years. It's a cross-section of the world, and that is the other piece that is important when we are engaged in ourselves into research. And I many times have emphasized this point that diversity is very, very important in our lives and in the science and technology that we practice. People from different locations, regions, ethnicity, gender. I think the diversity brings in different aspect and different type of thinking into this, and it's very important for research to be thinking about diversity. Now, when I was asked to give this talk, I thought, what a university is and what a university should be. What are the academic excellence, lies on? What is the fundamental platform that universities should provide? So I couldn't find a better context than quote Gitanjali from Tagore. Every word in that short excerpt that I put up kind of conforms to what a university should look like. The freedom of thought, right? Lack of fear, openness, going into the depth of truth. I think these are what we really should be aiming at for our students to learn. And as part of this learning process, they should all be part of a community that really looks forward out of the box towards building the next generation of technologies so that we live in a better world. And of course, in the background of all this is essentially the society, the people that we ultimately will create our discoveries as an impacting platform. So in many ways, I think this quote essentially captures the meaning of what a university setting should be. In fact, what you're seeing is actually a convocation at RISE, one of the culmination of long periods of research effort by students. And we all come together to celebrate that. And this is what happens in every university. And that feeling, that moment that we can capture, essentially condenses not just hard work and relationships, but also this whole concept of freedom. And I think that is very important as the foundational aspect of academic research. Now we can break it down, this whole approach to specific points. And if you look back into the history of discoveries and innovations, there are several points that come to mind. Of course, the beginning of all this is seminal ideas. Again, as I said many times, examples like quantum mechanics, foundational. So those are very, very important. And as we work with students and other faculty together, I think it's important to create these ideas. Even in industry today, there is this whole segment called ideation process. How do you really engage in research and development? Where do you start? So I think it's important to bring out ideas. And of course, the training is important so that the ideas are related to the contextual experience that you're providing. But of course, ideas, we all have ideas, right? How do you sustain ideas? And that's where the motivation part comes from, right? As a faculty, as a PI, this is what I always strive to do, right? How do I motivate my students? How do I keep them engaged? Because sustaining, these kind of ideas, after they are seeded, it's really a challenging problem. And so motivation is very, very important. And there are many different ways of motivating people. Of course, that will be a totally different talk in itself. But, I think the challenge that I have and throughout my career, what I've strived to do is to really try to motivate students and excite them so that these ideas are worth pursuing, right? And of course, then with these initial, starting points comes discoveries and breakthroughs. It doesn't happen all the time, for all of us know, if you're doing a PhD, perhaps there are 3 or 4 or 5 moments in our 5-year period where this eureka moment comes, right? Suddenly somebody finds something and, you really change the world in many ways. So it's important to capture those moments. And it's very important that the people around you support to take those moments into further aspects. So then, so from the ideation, you end up with discoveries which are important. And then it's important once you actually disseminate it to the public or to the community that it has to be validated. That validation period is also very important. We have seen many discoveries that ultimately cannot be validated. And obviously, that's part of the logical aspect of science. So that period could take maybe a short periods, in some cases, very, very long periods of time. And a good example is quasi-crystals. Right? After the discovery of this 5-fold symmetry in materials, there were a lot of discussions and a lot of pessimists thinking that this is really not possible in materials. But with time, people found experimentation that allows you to verify and validate. And that ultimately leads to the acceptance of this discovery. And then after that, of course, there is dissemination, acceptance, and then, it comes into various channels and it goes to the community, scientific community first, and then ultimately it goes to the public. So this is the foundational aspect of research, right? And then there is the applied part, So, of course, we are these days always thinking that some of the things that we do in our lab can be translated into important products and, ultimately commercialized. So again, that's a tricky part, and I'll maybe mention a couple of things later on. But taking innovation, inventions in the lab through a period of innovation to ultimately creating products is a very challenging and important proposition. And of course, that is where finally you create the products that ultimately impact society. So these are some of the points that are important for creating and sustaining excellence in any environment, particularly academic. Now, in terms of this interesting aspect of ideas and innovation, I just wanted to put a piece of an article that was published in Nature a few years ago. And of course, Nature is just one journal, but it's a good indicator of excellence in terms of publications. And this was taken, they actually divided the periods into different decades and essentially plotted the proportion of papers by decade and essentially put top 5. Very interesting that in the 1960s, India actually features prominently in that block. One of the blocks is India. Perhaps, after the independence, there were a lot of people returning from, places like UK and so on, and established labs here and created an environment of innovation and creativity. So they were able to actually be at the forefront of research and publications. And then as you go down the decades, you can see the transition happening, right? Of course, Europe was dominating the science and technology before the war. Then slowly it was the dominance of the US. And then some of the European countries kind of changed. Japan came into the picture. And now, if you look at the 2010s and 20s, China has come into the picture. And again, it's very obvious why this is happening, right? There is, because of huge amount of investment, resources available, this whole culture of excellence in research being created as a whole. This is what ultimately leads to this kind of prominence. So again, although I should take it with a pinch of salt, because it's just one journal that is kind of collecting some of the seminal papers that are published, but nevertheless, it's a good indicator, and indicator of how much investment has gone into creating foundational science. Now, I just want to mention one thing before going into some examples of this innovative kind of creative kind of ideas. And this is related to this applications, taking innovations and into the marketplace. Oftentimes people talk about the value of depth. And this is particularly relevant because India is now going through a phase where there is a strong emphasis on taking ideas and commercializing and taking to the marketplace. And the most challenging part of this is that, as ideas come, as discoveries happen, there is a certain period of sustained sustenance, and that is normally supported by federal agencies and institutions and so on. And then if you really want to take this and make it into a product, it needs a different kind of resources. And also, more importantly, this first phase of sustained basic research and validation has to connect seamlessly with the new resources that is coming in to take it and commercialize it. Oftentimes, it doesn't really match, and that's where the value of depth comes into the picture. So many ideas that, as you're trying to implement, either because they are too fundamental in nature, or there was no proponent to actually take it and really publicize it or make it a value proposition. Many times you fall into this value of depth and things will not continue. I mean, we have had experiences. For example, many years ago, when I was at RPI, we started a company on the idea that you can make flexible batteries and flexible supercapacitors. Perhaps it was too early, and it took almost, we sustained for almost 10 years, but it could not sustain afterwards, and it kind of died, right? Of course, maybe there are pieces of that still existing, but the point I'm trying to make is that oftentimes you need to have that confluence of the initial phase of research that actually validates the idea, and then this new influx of resources that comes in to pick up and build in a bigger way. In some cases, it has happened, extremely, well, and you can see those things being successful. But many, more than 90% of the cases fall into this value of depth. And now let me come specifically to nanotechnology. This is very dear to my heart because my entire career was based on this. And the long-term perspective of nanotechnology is essentially the fact that you are able to manipulate every atom in a structure so that you can create the flexibility in the functionality that you're trying to create. So that is a compelling argument that if you can actually understand and control every atom in a material, you have enormous flexibility, you have ultimate flexibility. And most of the efforts in the past 2 or 3 decades have been directed towards this whole idea of controlling matter at the atom scale, or even further at the electron scale. I mean, that's more recent. So, as you can see, the nanotechnology, again, it's based on a length scale, is now transitioning slowly into quantum technologies, quantum materials. So this transition is essentially going from nanostructures to atoms and molecules. My beginning on nanotechnology was when I was a graduate student, and essentially we were looking at small particles. Those days, the term nano was not even coined, so we call it small particles. But basically, the idea is the same. If I take a very, very small piece of matter and try to look at it and understand it, structure-wise, properties-wise, how is it very different from the bulk material? So there are 2 aspects of nanotechnology. Of course, one is this whole idea of fabrication, scaling down, processing. And then the other piece is that as you go to very small scales, what happens to this material? Is it the same as the bulk? And obviously that answer we all know it is not. And then the question is how easy it is to control the structure property correlation. Right? So the entire nanotechnology in the last 2-3 decades have been focused on this understanding of how structure and properties can be correlated, controlled, and built, from small to larger scales. And if you look at, technologies, the semiconductor industry has obviously, accepted this idea that nano is going to be the future in a big way, and they have pushed the limits of top-down approaches to a significant level. Maybe a decade ago, it would have been almost impossible to believe that you can actually do features that are less than 10 nanometers. But today, with all kinds of innovations in that industry, and again, it's a $1 trillion industry, so resources are plenty, people are able to push down the limit of scale to perhaps 7 nanometers today, and maybe even further. But there will be a time when you're not able to push this even further. So you hit a brick wall. If you look at Moore's law and things like that, it kind of plateaus because of various problems. And then there might be a way to think about it differently. And that is this paradigm shift from top-down to bottom-up approaches. How do you assemble things from the atom scale or molecular scale? So again, if you look at today's efforts in nanotechnology across the board, this is this synergy between the top-down approaches and bottom-up approaches. And it'll take a while to stabilize and see how technologies adapt with many of these approaches to really build structures at the atom scale. And the thinking about quantum materials, thinking about how materials behave at the very, very small scale, have been there for a very long time. Since the beginning of quantum mechanics, controlling matter at the atom scale has been the dream. Right? Whether it is Richard Feynman or people of that stature, always was really fascinated by this idea of controlling things at the very small scale, and not just controlling, but how things behave as you go to that kind of scale. And nature, of course, if we go further and further, millions of years back, nature has been in play to do this in a significant way as well. So here is a beautiful example of a nano composite. And if you look at this material, I'm always fascinated when I look at this material, because 99% of this material is calcium carbonate, which is just a chalk, which is so brittle. But if you try to break this, you probably will break your hand before you break this structure, because it has become so tough. And there is not, people have understood the structure pretty well. And it's all about really engineering at the nanoscale or atom scale. What this material is that you have these platelets of calcium carbonate that is sandwiched between proteins or soft matter, so that as the cracks run through, it doesn't really run through because it gets deflected so many times that the energy absorbed is very large and it becomes a very tough material. So, mimicking nature also is an approach of nanotechnology. And that really clearly gives you this access towards the bottom up of building things. So again, a beautiful example of nanoengineering and how materials can be controlled from nanoscale to build superior architectures and structures. Now, there's a practical aspect of it. There is a business aspect of it. Nanotechnology, there has been several studies on how the divergence of this technology is happening. This was something where I was involved to run a worldwide study a few years ago on how, where we are in terms of the understanding of nanotechnology and implementation. And you can clearly see that this 2020 to 2030 is considered as the divergence phase for nanotechnology, whether it is using top-down or bottom-up. The understanding, and again, this was done across the world, not just in Europe or US, but also in Asia. The adaptation is going to happen at a significant pace that the number of technologies where nano is involved will really exponentially increase. So it's a very interesting time frame in terms of integration and adaptation of nanotechnology. The last 2 decades have been mostly about single nanoparticle understanding and then some level of integration. But let's see how that will work. Now let me come to a little bit more specific that is very close to what we have done for many years, and that is related to the carbon materials and carbon nanotechnology. Now, again, going back to this particular, going back to this 2019 issue of Nature, and again, I mean, I just picked up Nature because this is a journal that we have a lot of respect for. And what in this particular issue, what they did was, over the years since Nature has been in existence, the journal, they just chose the top 10 papers, in terms of citations, impact, and stuff like that. And if you look at the list, it's really impressive, all the way from the detection of a strange particle, particle physics, to the advent of antibodies, the human evolution, the structure of DNA, obviously, or exoplanets. I mean, obviously, these are things that have really changed our lives. You can clearly see that. The impact of these foundational papers have been so enormous that what we do and what we think today is simply based on those discoveries. Among these 10, I was very surprised that there was a couple related to materials. The one that I'm not going to talk about is related to a class of porous nanomaterial. Now today, of course, there's a lot of talk about metal organic frameworks and COFs and porous materials, catalysis and applications like that really is focused on understanding the porosity of materials. But then there was another one, which was again very interesting for us, and that is the nano revolution spawned by carbon. And that is what I'm going to say a few things about. And this kind of coincides with the dawn of nanotechnology, right? If you think about the early 90s, when this whole investment was done in nano and the whole terminology of nano got coined, I think it kind of coincides with the discovery of fullerenes. And one of the things that we always appreciate is that the discovery was done at Rice University. And again, in some sense, we consider Rice as the beginning of a nano revolution, simply because of the discovery of fullerenes. But the discovery of fullerenes, and again, what you're seeing here, Richard Smalley and Robert Curl, the two professors from Rice, and there was a visitor from England, Harry Croto, who spent some time at Rice. And again, it's coming together of people with different backgrounds that ultimately made this discovery. Harry Croto was a spectroscopist. He was looking at extraterrestrial material, clusters and things like that. Smalley was a chemist, and Curl was actually a cluster chemist who were actually ablating material. But it proves the point that when people with different backgrounds come together, new things can happen. And this interdisciplinarity has become so important for research these days. Even, the example is the department that you just created, right? Department of Energy and Sustainability. 20 years ago, you wouldn't have thought that there would be a department called Energy and Sustainability, right? So the way things have evolved, changes things. And that's really a wonderful thing. Not only that it caters to the needs of the day, it also changes the way we think about things. I'm sure that faculty in your department comes from all over with different backgrounds, and that is really the essence of innovation. So, fullerene discovery, I will say a few more things. It's really a fascinating, discovery pathway, because if you think about the intrinsic material, it's graphite. It's sp2 hybridized carbon. Right, very simple material that existed in pencils, and we all are familiar with graphite. It's been around for a very long time. But then, from that parent material, why so much of innovation? Where did that come from? Right, and in fact, if you look at, I put three candidates here that have really, stole the limelight in carbon research. One is fullerenes, the C60, carbon nanotubes, and graphene. Right? If you look at these three materials, the one obvious thing would have been to actually pick up a layer of graphene first and look at it, right? Because graphite is made of these planes. That would have been the most obvious thing to do. But it took such a long period of interesting structures other than the simple graphene to actually get to that point. So that again, is a point that I want to emphasize. It's a case in point suggesting that discoveries are not really made in any particular linear fashion. It happens serendipitously many times. So, and also when you come to C60, it's even more interesting because the carbon-60 material was produced by many groups in the 80s. The cluster physics was becoming very popular, and people were actually ablating all kinds of materials and looking at mass spec to see what kind of clusters are formed. And in the early 80s, the Exxon group, in fact, had published a paper that shows the 60 atom peak of carbon. But they were not the people who actually got the Nobel Prize for the discovery, because they couldn't really understand what the structure of this material was. And so that the credit goes to the people, Harry Kroto and Curl and Smalley, who made that connection of what the structure could be. And it's even more fascinating because the soccer ball, which was the previous design, the 20 hexagons, 12 pentagon structure of soccer ball, was always there. It existed, and it's exactly the same structure, right? So why didn't anybody make that connection is the question that is interesting. And this is, I tell my students that this is a great story to learn from, because it's all about making connections. Of course, you have to be ready and trained, but how do you make these lateral connections? You knew that a 60 atom carbon was extremely stable and it has to have some specific structure, but it took really ingenious thinking to make that connection between a soccer ball sitting right in front of you and this perhaps a structure that could be. So that's again an interesting story. Other aspect of the fullerene story is that, these are called fullerenes. There's nothing to do with any of those people who invented the material. It's not Smalley, Curly, or whatever, right? It's fullerene. And why is it's called fullerene? Because there was an architect called Buckminster Fuller, his name was Buckminster Fuller, who was designing a particular type of structure. He is an architect called the geodesic domes. And because of the symmetry that he was looking at, he built these domes exactly like the soccer ball structures, because of the high symmetry this icosahedral structure has. And so obviously, after this connection to the soccer ball was made, people found, oh boy, this Buckminster Fuller architect is actually making these structures. And his name got drawn into this whole business. And he's probably the most famous person in C60, although he didn't have anything to do with fullerenes, right? So again, I want to emphasize this whole idea of the lateral connections, thinking sideways. And all the students who are actually involved in research should always be trying to think out of the box and looking at these connections, which ultimately will lead to something. And then, of course, there was a discovery of nanotubes, I'll say a few things. And then, of course, finally, graphene. And again, the reason why graphene got the Nobel Prize is not because they were able to peel layer by Scotch tape, but they were able to explore the beautiful physics in these two-dimensional layers of graphene, and after they actually made this structure. And so, again, given that my initial involvement in this nano after my PhD was on the carbon nanotube, I'll say a few things. Again, the serendipity is what strongly comes to the fore when people were really fascinated by C60 and many things that you can do with C60. After my PhD, I went to NEC Corporation, and the main focus was trying to make artificial materials through doping and stuff like that. So they were actually playing around with C60 for superconductivity. Unfortunately, many of the structures that were made were not very stable, but it was really pushing the limit of superconductivity. Even today, superconductivity is a really fascinating field. People talk about this graphene-based superconductors and bilayer graphene and so on. And even, room temperature superconductivity, perhaps the biggest hurdle for our technologies to see. And there's so many efforts along that direction. But so when I went to NEC in Japan, that was one of the main things. They were trying to play around with this new material, new structure like C60, and trying to do many, many things. Put atoms inside, put atoms outside for doping to make it superconducting. There was a whole range, and they were publishing papers left and right in these journals. So my boss, the person I was working with, Ijima, he was actually a microscopist. And again, as it's like a fire, right? As the fire rages, people sitting next to it also gets affected in some sense. So there was this, carbon mania that was starting to develop. And he was, since a microscopist and he had some experience in carbons, he wanted to kind of just look at some of these materials that came out of the electrode that was used to make the fullerenes. And again, the rest is history. So one day when he was looking, instead of these small zero-dimensional particles, he found these needles. And that was the beginning of another field. And if you look at carbon nanotubes, there are, I don't know, hundreds of thousands of papers published in the last 20 years. And the first paper that was published was this multi-walled nanotube structure in the 1990. And then me and Professor Ijima kind of published the first small paper called the smallest carbon nanotube. We actually didn't call it the single wall nanotube, but essentially suggested that from microscopy, you could actually see glimpses of the single layer nanotube. And after that, there were so many papers from different groups, and the whole field exploded. And also, the nanotube was very unique because of the structure property correlations. The fact that you can have a small chirality in the lattice gives it very different properties, all the way from a semi-metallic carbon to semiconducting nanotube. Was a remarkable thing. And again, it is one of those milestones in nanotechnology, suggesting that you can actually tweak the structure a little bit and get a significant change in electronic properties. So the nanotube really took the place of fullerenes, and you can see these beautiful structures. We were one of the first to publish in Nature, suggesting that you can actually make them in large quantities and things like that. So again, the rest is history. Many of you know this. So much of work being done, and slowly you are seeing a phase where nanotube is being translated into important technologies. And the next many years you'll see that. And then there was also, again, this creativity. I want to emphasize when we talk about basic science and foundational research, creativity is important. Think out of the box. That is one thing, in academic research, although we are now quite interested in translation and so on, fundamental research is still what makes academic, infrastructure. We cannot compete with companies to make competitive products in a short period of time. That's why the foundational research has to happen in universities surroundings, and it has to be taken up and developed by other people. And I already told you this, whole period that finally takes its course. So this is a great experiment. This is one of those results that that always in my mind, because we were able to publish this paper in Nature in about 2 days' time. Not published per se, but accepted in the Nature. We submitted it, and 2 days later we got a review saying that it's accepted. Right? Never happened to me in my life before or after. So the idea was that I was playing around with this carbon nanotube and some metals, particularly to increase contrast, because if you deposit some metals, you can get better contrast to image. And then you did some annealing. And one day when I was looking at these samples, I saw that the metal, and again, I used whatever metal was available, which was lead, melted during this annealing process. And not only that it spread on the surface, but it actually got into the channels of the nanotube. Well, so we called it the filling, capillary filling. It actually published with a cover page of Nature. But again, something that I was not really looking for something like that, but you see these. And then the important thing, as I said, was to make that connection. How did it happen, right? So as a student is looking for something, he has to have his eyes and ears wide open. And I think that is very, very important. Of course, we went on to do all kinds of things with nanotubes. There's 2 Guinness Book of World Records, smallest brush that we were able to make, the darkest material. I'm sure that you have actually seen some of these things. And but at the same time, this path from fundamental discoveries to practice is a long and tedious and sometimes very challenging problem. And it could take a long time in some cases. During the early days of nanotubes, Richard Smalley, who was fascinated by this material, he was, again, the Nobel Prize winner for fullerenes, said, I want to do things like, I want to really spin a fiber that is long enough that I can do fishing, the strongest fishing rod, right? Or there was these crazy analogies to like the elevator to space. I think there are still some projects going on in the world trying to make long nanotube fibers. But the actual practice or the actual translation of an individual nanotube which has enough mechanical properties to something that is large and scalable is really a very, very challenging problem, right? And it's taken 2 or 3 decades now for people to actually spin continuous fibers with nanotube. And even those fibers, because of the interface problems and so on, are not strong enough to actually use it for the elevator type of application. So again, the point I'm trying to make is that from discoveries to actual practical application, it could take a long time. And we need to be patient, and we need to actually invest and support those foundational research and the sustainable research for long term. And there's no better place than academic environment for doing that. And the world is changing, right? The world is changing significantly. It's not the same place where I was a graduate student. Things are getting integrated, things are getting more complex. You're going to see all kinds of fascinating things, all the way from electric vehicles to responding materials to artificially created architectures that are extreme sensitivity. So there's all kinds of beautiful things happening in material science. And of course, material science is just one of those topics, but certainly feeds into many other things. Even, you look at one of those chips today, it's much more than what the Moore's law had predicted. So rather than going vertical, where you're scaling down device size, you're also going horizontal, adding more components, integration, multi-functional integration, things like thermal issues, thermal management materials, biosensors, actuators. So the new chip is going to be very heterogeneous and very complex. And this integration, when it comes to smaller and smaller scales, becomes very complex. So I think in terms of the role for materials in the future, it certainly has to go all the way from the small scale to larger scale. And working and collaborating with people of all expertise is important. And again, as your department, as it is growing, you're seeing people with different interests in different scales coming together, right? All the way from fundamental science to system integration. I mean, it's very, very important in the future to have departments that contain all these people. Maybe I have like 10 minutes or 5 minutes.
Yeah.
So again, the idea of this bottom-up approach is very compelling, because that's the only way you can really create materials from atoms and materials from molecular organization. And this becomes very, very difficult when you go to very small scale, because you are not able to pick and place one by one, because it will be extremely time consuming. So, again, you will see in literature many such cartoons that kind of tells you like a wish list of what you want to do. It has nothing to do with the actual ability to do things like this at this point. So how do you really build three-dimensional complex structures with various types of nanomaterials? That's going to be really the big challenge that we will have in terms of the material science people. And I have to say that there are several interesting examples that we and other people have done in this field, particularly for integration. So this is a very interesting example of a graphene material that has been cross-linked and created into a three-dimensional structure. And when you can do that, you get materials that are really remarkable, with huge range of thermoelasticity. This graphene foams that we were able to create were extremely elastic at cryogenic temperatures, as well as at 1,000 degrees Celsius. So again, the power of nanotechnology and nanomaterials is that if you can design and build and engineer these materials in a right and have remarkable range of properties that otherwise cannot do. And then there are interesting approaches that has come into the picture. 3D printing, everybody's familiar with additive manufacturing, right? So everyone knows this. And perhaps additive manufacturing is the first step towards realizing this bottom-up manufacturing in its full strength, right? Essentially what additive manufacturing does is you lay things layer by layer and create whatever design you have, and it's all run through robotics and interface, data interfaces. So it's a beautiful example of how this bottom-up manufacturing can evolve. Of course, the challenge in terms of the 3D printing or additive manufacturing is the length scales. So you still are restricted or limited to the micron size or hundreds of microns. So if you can actually fine tune these and create materials that are much finer in scale, the real bottom-up manufacturing paradigm could be achieved. And here is actually a very recent example that we did. Again, it's not as simple 3D printing. It's this 2-photon polymerization approach where you can get very, very finer features for 3D printing. In fact, we were able to print glass. And in fact, we were able to print quartz at very, very fine scales. So again, innovations, creativity, improvement in instrumentation, facilities, all these things add value to what we can do and how we can change the world. Again, nanocomposite is another area that we have worked for a long time. I'll skip this. But again, I wanted to point this out because you might get in many of these scenarios things that are quite unexpected. What we did was we created this carbon nanotube polymer composite, and we were doing dynamic loading on this material. We found that the strength actually is increasing with time rather than decreasing. And the reason for that is the nano interface is very complex and it can reconfigure dynamically. So I showed this example just to kind of say that there are many materials that can be dynamically tuned. So, most of the time we look at materials that degrade with time, but why not think about or think about a design where the right kind of reconfiguration increases its strength, right? It's kind of a out of the box thinking, but there are examples in nature. Your bone is a good example, right? Kind of continuously increases as you lower. Of course, part of it is metabolic, but the question is really artificially, how much can we do, right? So there are really fascinating things like that in nanotechnology. And the reason why it becomes very interesting is that when you go to nanoscale, there's a huge amount of interfacial volume that you can play with. And finally, I cannot, diminish the importance of resources and the infrastructure. Many of the things that we do, we're able to do because we have state-of-the-art machines and instrumentation. My graduate study used to be in microscopy, electron microscopy, but I can't even use one of these new ones. Right? It's $5 million microscope with energy filtered imaging, aberration correction, so that you can really see every atom that comes into a material. So it's not just about building things with atom, but also seeing every atom that is in the structure. Right? So this is a two-dimensional alloy of 3-component system: molybdenum, tungsten, sulfur, and selenium. And essentially, by the right kind of imaging, energy filtering, machine learning, so that you can extract information at very high detail, you could tell the position of every atom in the structure. So that level of complexity is also important because you're trying to understand. If you're trying to build things atom by atom, you should also know where the atoms are sitting, right? So again, this is just one example of a 2D layer, but I think it's very, very important to realize that these instrumentations are important. And again, I'm not saying that these instrumentations should be there in every lab. This is the reason why we should come together, have central facilities, and work together to be able to do things like this. I'll skip a couple of things related to the 2D materials. I think I gave a talk here a few years ago, and I had these. But again, there are very, very fascinating materials that can be heterogeneously integrated at the nanoscale. Here is a really beautiful phase diagram that we have pursued for a long time, the carbon, boron, nitrogen phase diagram. The reason why I keep talking about this phase diagram is because you have many, many compositions and phases that really are important. The carbon by itself is very, very fascinating. And not only that it is interesting for graphene, but it's also interesting for diamond. It's a cubic material. And similarly, there are cubic phases and hexagonal phases in this phase diagram that really has value. There are hard materials, there are flat, soft materials in this phase diagram. But what we also realize is that when you're trying to bring multiple components and trying to build structures, they can also have local phase separations and so on, which becomes very problematic. So if you're trying to grow a boron, nitrogen, carbon material, you have these segregated domains of boron, nitride, and carbon. And again, it has got its benefits, but it's also interesting that from the point of view of controlling materials at the atomic scale. So let me skip these. So this is the final experiment that I will show you. Again, the idea of innovation and idea of thinking beyond what you're looking for, right, is very, very important in research. So this was actually a work done in 1996 after I moved from Paris to Stuttgart. And they had this huge microscope. It was kind of a 1 million electron volt microscope that goes 2-3 floors. The good thing was that it's got a lot of energy. The electrons had a lot of energy, so you can hit materials with these beams and transform them. I mean, typically, people have looked at transforming materials using electron beam. So you take carbon, you hit it with the electron beam, and they form graphitized structures. That's understood. But what we did, without really knowing it, is that we did this experiment of irradiation at a higher temperature. I mean, there was a heating stage, so we just wanted to try it. But then when you did this at higher temperature, what you're seeing is a very, very strange meta-stable structure. In fact, if you look at the actual separation between layers in graphite, it actually is decreasing as you go towards the inside of the structure, which means that the material is getting compressed to the core, right? I mean, in fact, the compression was so large that if you were to translate to actual physical pressure that you need to actually compress graphite, it'll be 100 gigapascals. So it's a self-assembled structure, but because of this heating involved, the defects were able to play a key role, and the material got self-compressed. In fact, when we continued this experiment to keep irradiating at higher temperature, you start forming diamond in the core without doing anything, right? It's an irradiation-induced formation of this diamond particle in the core of this graphite material. Again, it tells you many things. One, by serendipity, you can get to some very, very fascinating things. It's a phase transformation that you can observe in situ in the microscope. So that tells something about what instrumentation can do. And you can understand things happening in real time. And that is very important. A lot of experiments these days are in situ experiments, stages where you can actually observe chemical reactions and phase transformation, things like that. So again, I'm trying to build the story that there are multiple things that are needed to create excellence and create the best output that you can produce. There are many, many examples. And again, I had this slide. I probably will skip this. But you can see, the story of the lithium-ion batteries, right? It started in 1970s. In fact, Stanley Whittingham demonstrated the first metal battery in the 1970s. And it took almost 20-25 years before it was first commercialized by Sony. And actually to make, bring this into practice, it took even a couple of more decades, right? It's only in the last few years that the lithium-ion battery has become so powerful, especially with EVs and other computer equipment. So one thing that I would want to suggest is to have patience in this whole business. Foundational work is important, but also many of these big applications, evolutionary changes will happen with time, 20 years, 30 years, depending on the systems and so on. So I think that's going to be my last slide in terms of example, and this is my last slide. I was trying to put all these things together and create maybe a message. And to me, this whole idea of sustaining excellence and in an academic environment, it's more like a tetrahedron. So the tetrahedron has 6 edges, 4 corners, and 4 faces, right? And if you can bring that together, that really is what the environment, ecosystem should look like. And I already mentioned the edges are the ideation and knowledge, the innovation or sustaining excellence, motivation, creativity, of course, training. Without training, you cannot achieve this, and translation and societal impact. These are essentially the edges that connect the innovation ecosystem. But then there are the corners that are also very important. And those corners are facilities. Without facilities, you can't do much in these days, especially in areas like nano. Human resources, and you don't have any problem with that here, excellent faculty and students. I believe leadership is very important, right? Leadership has to realize what is it for the long term and the short term and the midterm, right? You cannot really focus on short term and forget the long term, because that would be a disaster in my opinion, right? So how do you really, make resources available for all these constituencies? I mean, I think, time and again, it has been proven that the big innovations, the big technologies has come from some foundational work that has been done in universities and places like that. So leadership is very important, and incentives. And again, that's a tricky point, but incentivizing things that people do, even through simple things like motivating somebody or giving a pat on the back or announcing somebody's name in public. I think all these things are easy things we can do. And then there are the facets, right? And the facets are also equally important. Collaboration. These days, we collaborate with so many people. I can't even think about how many people we have, published papers with and collaborated over the years. And interdisciplinarity, I think that's quite obvious, and it's becoming very popular everywhere. And visibility and outreach is also important, right? Again, we are not isolated entities doing something and forgetting about it. We have to, I was actually having a chat with Ashish. How do you really disseminate our ideas, and how do we really, provide information to the outside world, to the people surrounding us, to the society in general, schools. We actually put a lot of emphasis in universities in the US on how we can create this ecosystem where we can actually let people know, get students motivated at all levels, K-12. And that's very, very important. And finally, funding, of course, that's part of our job here, to generate resources. I just wanted to kind of mention the one last thing about our department. This is actually an interesting thing that we did. We created a new department of material science in Uprise in 2014. For 6 years, or maybe 7 years now. I mean, we went through all these challenges that I mentioned, in terms of resources, in terms of funding, finding the right people, getting students, and we're still facing that. But end of the day, it is the excellence that matters, right? This is a list of, again, there's no relevance to what I'm saying specifically, but it just shows how, what scholarship is all about. You can have small numbers, but a very, very impacting set of outcomes. And that is when people will notice you. And again, it is not done by staying separate unity as an individual unit, but collaborating and helping each other and building teams and so on and so forth. And that's what excellence is. In the end, the question about what excellence is, I was reminded about this when recently one of my students asked me this question. So she asked me, so Professor Ajayan, do you actually dream your research? I was never being asked that question before, but and she said that she was actually dreaming about some of the things that she was doing in the lab, right? And that is what excellence is, really, engagement, involvement, essentially being part of this. And I can certainly see that kind of vibe among certain groups of people at IITs and many other places. But on a larger scale, can you achieve that? That is a big question. And how do you achieve that? That is, again, a discussion, a dialogue that you should constantly have with the leadership, within your departments, within your community. And that will ultimately make a place successful. So thank you very much for listening. It's a very different type of talk, but I suppose you enjoy it.
Thank you, Professor Ajayan, for a wonderful, lecture. This should be very motivating for the students as well as all the researchers and faculty members who are there present listening to Professor Ajayan. So I'll now take a few questions. So one of the questions which has come from Kedar Yadav, where does 1D carbon chain stands in terms of carbon nano world?
Yeah, so it's again a very specific question. So there is always this question about, you have the fullerenes, the nanotube, the graphene, and what is next? So there's been lots of predictions about, single, triple bonded chains of carbon. It's been very similar to the polymer systems, I would say. Of course, you can have better mechanical properties or interesting electrical behavior also. But again, from prediction phase to actual large-scale experimentation to validation, it could take time, and in some cases, it may be even not possible to make. Right. I mean, every one of these carbon materials, fullerenes, nanotubes, graphene, the big thing came when somebody was able to large-scale produce them. In the fullerene, I think a lot of people didn't believe after the discovery, and then Tashmer and Huffman figured out that you can actually dissolve C16 organic solvents, and that changed the field. The same story with nanotubes. We were able to show that we can mass produce. That changed the field. But graphene is the same story. Very large area growth of graphene and copper changed the field. Right, so it's very similar. Depends on how well people can manufacture it.
So, Professor Gautam Dev has a question. So, so the challenges and hurdles you faced while taking your department as a world-leading department.
Well, it's still not a world-leading department. We are very small. But again, as I said, we started off with about 5 people. We hired a few more. We lost a few. So it's a dynamic equilibrium, right? And you constantly fight for resources from upper administration. And we constantly engage our young people to whatever opportunities that they have. We try to pat them on the back all the time. And it's a process, I think. But again, I think the key point I was saying is there, right? I mean, excellence. How do you really cultivate excellence?
Right.
Push them to keep high standards, publish in high journals, or get into translational work if that is what interests them. And we all collaborate. Actually, I think I must have published with every faculty member in the department, and the same happens with many people.
Right.
So collectively, sometimes these days, especially, it's much more easier to make that impact.
Mm-hmm. Right. So another question is from Rajesh Kumar. How does the graphene layer? How number of graphene layers improves the properties of graphene aerogel?
Well, I mean, again, I don't work on aerogels per se, but I suppose as you increase the number of graphene layers, the electronic properties have significant differences. We want monolayer graphene because it has gotten certain specific mobility and electronic structure. But if you make larger, layers, it becomes more like graphitic. Right?
Mm-hmm.
It becomes more graphitic. The density might also be different.
Right.
But maybe, there are specific number of layers that have some magic properties, like these, twisted layers and so on.
Right.
But that's a complex problem.
Okay. Yeah, I mean, material science is quite complex in that sense. Right. So Professor Dhirendra Katti has a question. Generating more ideas, that is in the form of patents or papers, versus taking a few ideas to prototype or commercial technologies, which path would be a recommended path in your opinion?
Well, as I said, I think both are important, but I believe very strongly that the academic environment is most conducive for basic science, right? And, the students who come, they have limited knowledge about the practical aspects, and competing with industry is challenging. But again, there is no limitation in the sense that someone can come with a brilliant idea and change the world. But it's a long route towards that. Absolutely. I really believe that, academics should focus mainly on foundational aspects. But there might be exceptions. I mean, there are places like MIT and Stanford where they've created an ecosystem, making it easier for students and faculty to, go out and build stuff. But that is not true for all universities. I mean, I wouldn't say the same with Rice University. Right? We don't have the ecosystem yet. When if IIT Kanpur wants to build that ecosystem, it's not a bad idea, but it's a long road, right?
So I'll take one last question. I think we're running out of time. So I'll request all the audience persons in the audience to email to Professor Ajayan if they have any specific questions. His email ID is pma2@rice.edu, but you can find him on website as well. So the last question is, what is your comment on the van der Waals heterostructures of sp2 nanocarbons?
I think it's again, people have been thinking about this for many years now. There are exciting opportunities, but also challenging problems in terms of building these things. The biggest thing that came out was this twisted bilayer superconductivity. The question really is, can you practically achieve this? Because, to control the orientation or control the angle between two layers through processing like CVD, it's not a thermodynamically feasible thing to do, right? Because there is always going to be, I think, a kinetic factor that spoils the deal, right? So, I mean, maybe the only way to do this is to really grow single crystals of large area, like graphene, and stack them physically. But again, that will not be done yet.
So with this, I think I'll close the question answer session because of lack of time. But let's thank Professor Ajayan for a wonderful lecture, and I'm sure there are a lot of things which he said makes a very important connection with what we do in IITs and how we should grow into a world-class institute in the long term. So with this, I'll request Professor Kalol Mandal to say a few concluding remarks.
Yes, it's our pleasure that you are here, and the talk what you have given, and it's getting eye-opening for many of us, I would say. And thank you very much for coming and spending some time with us. And I would definitely reach out to you.
Thank you so much.
And I request Professor Harish to present a token of our appreciation to Professor Ajayan. Maybe you can take a photograph.
Oh, thank you.
Professor Ajayan, it's wonderful. Thank you for a very much, and hopefully we'll be more connected. Yes, looking forward to collaborating.
From the department.
So there is one more gift from Professor Kalol Mandal.
From the Department of Material Science and Engineering. So this is one.
Sir, please.
Like giving a gift to your own people. I'm part of your department.
It's not that. Giving a gift to the person who, what we wear.
And this is
a jacket, with the department name.
Thank you so much.
This is another one from Energy Science. And
Sir.
I need to know more departments.
Thank you.
Thank you.
So much. Thank you, Professor Harish. Thank you, Professor Mandal.
Thank you.
And thank you.
I mean, it's unusual times, right, where we are just beginning to get back to normal. So
I also would like to thank all those who helped in organizing this event.
yes, absolutely.
So with this, we will close the today's session here. Thank you very much.
Thank you.